Today we're at the lovely Rosati's Field, Clifton Heights. Famous Rosati's water ice across the street. That's why it's known as Rosati's. What we're doing here today is we are going to long toss, my son and I. He's a pitcher for Devon Prep High School, and this is to help build up his arm. Well, that's what they say long toss is supposed to do. That's a whole nother study we'll look at another time. But the reason I like this field is that you look around and they have marked out how far some things are. Like, for instance, they have, this is 183 feet, and it goes to 190, and so on. Left field's 240, 280 in left center, 300 in center field. And what we do is we work our way out and see how far you can throw. We mark it off, go back from the fence. It's easier to measure that way. And we'll do this. And then what I'm going to do is I'm going to record this. And I also have, I coach summer team, and I probably have 20 to 30 kids that I do this with. And then what I'll do is, because this chapter happens to be about where do you fall in a distribution, what percentile do you fall in, instead of just giving somebody one number, what you do is you rank them according to where they fall in the distribution. And basically we'll do that, we'll convert it to a Z-score so we can compare it to someone else if they're throwing in meters and things like that. So there's all sorts of things that we get to do. We're going to be converting the distribution by multiplying or adding a constant, multiplying by a constant to see what happens to our distribution. So you'll see my son over here is now, he's warming up, getting ready to go. I have some video of us throwing, show you a little bit about that. Do a whole warm up, and then we'll go home and analyze the data. Go ahead, we're throwing it 120 feet out to the orange bucket out there, trying to reach into the bucket. I'm sitting out back looking over the data I collected. You notice that throwing a baseball is a little more involved than just going out and having a little catch. Long toss is a long process. One thing I've learned after all these years, a great saying is, you throw to warm up, you don't warm up to throw, and that's real important when you're trying to throw the ball as far as you can. So I collected data from 36 different baseball players throughout the years. And again, the long toss, the jury's still out on whether or not this really increases velocity. And that's what people are trying to do when they long toss, is increase their velocity. We're going to assume right now that, yeah, it does, but we'll do another study later on, and we'll analyze the data a little further to see how true that is. We'll test that hypothesis later on. But right now, what we're concerned with is we're going to try and find the position that any individual piece of data falls within the distribution. So how do we do that, right? Describing the location in the distribution. We do that with percentiles. And this is a real simple math equation, and it doesn't get much easier than this. If I wanted to find out there's 36 people, well, what percentile is this 290? Well, there's 35 over here. I do 35 out of 36. Rudy threw, my son, he threw here in the 260s. So I count how many are down here. It's 27 out of 36, which puts him at the 75th percentile. So whenever you hear that, that's basically what it's talking about when someone gives you something as a percentile. They're saying that this percentage of people scored below you. You can do it for any individual point within your distribution. So you should know anything down here is going to be less than 50%. Anything up here is going to be greater than 50%. So that's the first thing I wanted to talk about. The second one is going to be using a cumulative frequency graph where we can estimate people's percentiles, and that's what we're going to look at next. The second thing we're going to talk about in this section is how to estimate percentiles and individual values when we're going to use a cumulative relative frequency graph. You've seen a chart like this before, and this is a frequency table. But in this case, not only are we going to look at the frequencies, which is here, how many are between 190 and less than 200, 1 out of 36. Relative frequency is percentage. Cumulative relative frequency. Cumulative means to accumulate. Often you'll see that with snow or rain. They'll start in the beginning of spring, and then as it goes along, how much did you accumulate? So it piles on top of the other. So where does this 3 come from? 1 plus 2 gives me 3. Then I take the 3 plus 2 to get 5, 3 plus 8, and so on. The last number in this is always 100, 36 out of 36. And if you're looking at it that way, it's saying, well, what percent of people throw less than 300? Well, all 100 people were throwing less than 300 feet. And from that, you draw a graph. It looks like this. Now you could draw a relative cumulative frequency histogram, or you can draw it as a line graph. I drew it as a line graph. And here it is here. And as you go along, what it's telling me is from the different distances, what percentile they scored at. For instance, right in the middle here, 250 scored at the 75 percentile right there. You can find, these are all basically estimates, and you can find any of them along the way from 200 all the way out here to 290. Now what we've been doing is finding the percentile for any one individual piece of data, and that allows us to know within the distribution what percentile we scored at. So what percent of people scored less than we did, or threw the ball not as far as we did, whatever you want to say. This distribution happens to be symmetrical, and when we say symmetrical, we talk about having a bell-shaped. This distribution here, and in those distributions, the mean and median are the same. They're both right here in the middle. In a distribution like this over here, this one is skewed to the right. What happens is the mean is pulled towards these data points down here. So the median will fall here and the mean will be slightly larger. This is the opposite. The median will be down here and the mean will be pulled towards these lower values. And you'll see later on how that affects our calculations and such. We want things to go towards the normal curve, they call it. So what we're going to look at now is we're going to compare things to the mean. And in this case, you can tell that the mean's somewhere in here. But we're going to actually calculate the mean. We're going to use the mean and the standard deviation. Mean is x bar, not just x, and standard deviation is sx. Usually your one particular throw that we're talking about, in this case my son's throw of 260, that's your x. That's just your plain old x. X bar, which we can use the calculator to calculate, and I'll show you that rather quickly. I jump over in here, even though I already did it. I go into my lists and I put all this data in. Now I put it in L3. I just put down all the different distances that someone threw a ball. And then I put down how many people threw the ball that far. Now, what I do is I do stat, calculate. I'm going to do one variable statistics. In here, in my list, is L3. The frequencies, how often each one threw one of those distances, was in L4. I go down, I hit calculate, and it gives me to it. So really, essentially what it's doing is it's multiplying L3 times L4, and then it's dividing by however many there are in L4. So this is my mean, and this is my standard deviation. This is also standard deviation. We'll talk about that at another time. For now, we're just going to use this and this. So let's go back, and what we're going to do is my X bar was 240.6, and my SX was 22.8. So what does this information? What we're going to do is we're going to standardize our score. We're going to see, well, how far away, how many standard deviations away from 240 is 260? And how you do that is you use this formula right here. It's known as a z-score, standardized score. You're going to take your score minus the mean and divide by standard deviation. So in this case, I'm doing 260 minus 240.5 divided by 22.5, and I'll get a z-score. My z-score came out to 0.87. When I go back in here, well, why does that help me? Well, what if someone said to me, well, and this is my son's friend, and he says, well, I can throw a football further than you can throw a baseball. Comparatively, the distribution might not look like this. It may look like this or this. And what you want to know is, well, how many standard deviation? Who has a bigger z-score? You want a larger z-score because then you're either closer to the mean here or you're further away from the mean in this direction. And then you can compare two distributions that aren't related at all. So if I go down here to a football throw, and Aiden tells me he threw the football 60 yards. And that had a mean, an X bar, of 48 and a standard deviation of 14. So what I want you to do is use that formula. You can stop it, rewind it, look at that formula. You're going to do their throw minus the mean divided by standard deviation, and then you're going to compare those two and see which z-score is larger. We have one more final thing to look at, and I really enjoyed this. This is a lot, but I really like this information I'm about to give you because it makes sense. And you see how we can really start to get into analyzing this data.